You all finished the project, right? I'm assuming. Yeah.
Most people.
Thumbs
Did anyone
up,
not finish the project?
Yes,
Everyone.
where did everyone go?
I don't know. I'm really sad. You guys need to like keep pushing your friends to come to ops. It's really sad. Okay, we're gonna get started. I know our last lecture ran a little bit late, so hopefully this one is gonna end at 8. But yeah, we're gonna be talking about capacitors, ICs, and your next project.
I'm not in the right place. Okay, now I'm in the right place. That'll go away, right? It does. Okay, we have a few announcements now before we get into our lecture. So the first one is that there's going to be a PCB design workshop. So our workshop leads are super excited about this one, PCB design. So PCB stands for printed circuit board, which looks kind of like this. This is what all like motherboards and computers and basically like a breadboard, but instead of using wires, the wires are already printed into the board. So then you just put the components in there inside of them, and it's already all connected. So this is a really awesome skill to learn. It's important for future projects, future classes, and in the industry. So if you want to come to this, I really recommend it. The RSVP will be released in the workshop's Discord channel sometime soon.
Secondly, we're not going to be having a lecture next week. Instead, we're going to have a work session because you guys are going to be working on your fall capstone project. It's going to be next Friday, I believe, from 6:30 to 8. So come out. We're going to have a fun time. I'm trying to bring ice cream, so that's something. Also, the IEEE ice blocking thing is going on right afterwards, so you guys could just
we'll walk down together and have a good time at that too. So.
That's next Thursday.
Yeah.
The next Thursday. My bad. I don't have a calendar in my
next
house.
Thursday.
My
Yep.
I think this is the same time as the PCB workshop.
Yeah, it is also. So if you go to the PCB workshop, you don't have to come to this.
This is just like an external thing that.
Is that the lab?
Yeah,
it is
it's an
going to be
IEEE
a
lab.
yeah. Okay, so previously on ops, we learned about circuits and schematics, calculating resistance and equivalent resistance using parallel and series resistors. We also talked about Kirchhoff's voltage law and the current law and circuit debugging.
And this time on ops, we're going to learn about capacitors, integrated circuits, 555 timers, and announcing our latest new project. So fun. So first off, we're going over capacitors.
Okay, so a capacitor is essentially two metal plates with some sort of material in between that we call a dielectric material that conducts electricity across it. And what a capacitor does is it stores charge on either side of it. And you can think of it as a capacitor slowly charges up and turns into a voltage source, and then eventually it can discharge exactly like a voltage source as well. So it's a really, it sounds a little bit complicated, and it's definitely more complicated than a resistor. However, it can be really helpful in your circuits and designing other sort of functionalities. In terms of a capacitor, some important things to remember is that capacitance, which is the ability of a material to store charge, is measured in farads. Generally, a capacitor is in the pico to nanofarad range, so it's a really, really small value. And again, the most simplest form of a capacitor are these two plates, metal plates, that are separated by a specific distance in between. And then generally your capacitors are going to look like cylinders because they're just metal plates that have been wrapped around. So it's a little bit easier to use.
Yeah, which is what on the last slide. So how do capacitors work? So the way that capacitors work is that electrons will flow through the circuit normally, as circuits do, but when they get to the plates, the electrons can't pass through. There's no like wire connection between the capacitor. But instead what will happen is because the plates are so close to each other, the electrons on one side of the plates will build up and then push the electrons on the other side of the plates basically through. So it will act as though it is it'll act as though the circuit is still connected until all the electrons on the other side of the plate are all gone, and then that is when the capacitor is then like charged. And then it will then be able to discharge the electrons that are then stored up on the one side of the plate will be able to go the other way and discharge those electrons. That's like the basic way of thinking about it, and which is why it's configured in two plates.
And one other thing to remember is that unlike a resistor, which which didn't vary with time, a capacitor is dependent on time. And so here, at the beginning of our circuit, this capacitor has no charge across it, and therefore this essentially is an open circuit. However, as time goes on and as electrons and...
A closed circuit at the beginning, at the end it will become an open circuit.
Yeah, my bad. It just acts like a wire. And then as we go on, charge begins to accumulate on either side of the plates, and therefore you have an open circuit.
And so in circuit schematics, you'll see capacitors represented like this. So if you see one with this curved sign right here, that means that it's polarized. So just like an LED, it will mean one side it has to be positive and the other side has to be the ground side. That's what it means when you see that. But when you see someone like this with just two flat ones and no plus symbol, it means that it can be used in either orientation, like a resistor. And then here are the examples of like basic circuits. So this is the original one right there with the switch just open right now. But then if we connect it to A, it will flow into the capacitor and charge it up. And then once it's full charge, if we then turn the switch to the B position, now it will discharge. So before current was flowing this way through the capacitor, and then once it charges and we flip the switch to B, it will discharge the opposite direction back to ground the other way.
Okay, perfect. So we've already kind of discussed how capacitors work, but the first important concept of a capacitor is how it charges. So again, the opposite charge accumulates on each of the plates, and then as time goes on, the voltage across this capacitor increases. And then the time, let's see here. Yeah, so eventually at some particular point, we're going to have the voltage across this capacitor be equal to the voltage across this source here, which is, again, a really nice way to create a voltage source without having to have without a battery. Well, you would need a battery first, but anyways.
Yeah, so when the capacitor has the same voltage as the battery does, it means that it's fully charged. And as you can see by this graph right here, it shows the voltage in the capacitor over time. So when we start charging, it will go up really quick, and then as it approaches the voltage of the battery, it will slow down when it's charging. And now when it's discharging, the current flows from the plate and then back through the circuit to ground, and it's fully discharged when the capacitor has no charge left, or no voltage left. And so it will discharge at this formula here. The current of the discharge will be equal to the capacitance times the rate of change of the voltage. So basically, it will discharge very quickly at t equals 0 and then more slowly. So same thing, but the opposite way. It goes fast at the beginning and then slow at the end. And here we have this GIF here, which shows how it acts charging and discharging.
So here are a couple of capacitor equations. We won't go through the derivations of it. However, it's important to note that a capacitance or a capacitor is related to the area of the plates and also the dielectric constant. So you can adjust a capacitor and its capacitance value dependent on those types of parameters here. In addition, the current is given by this rate of change equation. So the charge, the capacitance multiplied by the change in the voltage itself is going to give us the current of the actual circuit. And then another important concept to understand, this is probably the most important to you, is time constant. This is referred to as tau, and it's equal to the resistance of the circuit multiplied by the capacitance. And what tau means is it's just the amount of time that it takes for the circuit to completely charge up, or for the capacitor to
not to completely charge, to charge to 63% of its max charge.
Yeah, so
that's very important. It has to do with the math of the formula. It's kind of weird, but yeah, that's what it is, to charge to 63% of its max charge.
Yeah, so if you wanted the capacitor to fully charge up, then you would have to have 5 times tau. So 5 tau is a really important number to remember, because again, it's the amount of time that it takes for the capacitor to fully charge up.
Awesome. And now when we're looking at capacitors in series and parallel, we want to find what they're equal to, like the equivalent capacitance, basically, just like we did with resistors. But this time, unlike resistors, it's actually the opposite. So in series, when you add them, it will be 1 over C1 plus 1 over C2 plus 1 over Cn all over 1, just like it was for resistors, that was when it's parallel. So it's the opposite, and then same thing for now. So now when they're in parallel, you just add them, C1 plus C2 plus Cn.
Are there any questions so far about these equations that we just went over? Yeah, go ahead.
What's the difference between like using capacitors and using like battery? Because like they're kind of like the same thing, right?
Sort of. So a battery can store charge just like when it's not connected to anything, it's stored charge and it's storing it in chemical energy. Capacitor will always like immediately discharge what it has as soon as it's given the opportunity, and it will discharge like way quicker than a battery. So a battery has higher capacity and better ability to store it. Capacitor has less capacity and like will discharge. Yeah.
Yeah, and also in a lot of circuits, you want to use capacitors and resistors to create filters and stuff like that. And so you're not going to want to use a battery because the capacitors also have different capabilities as well. And you'll learn more about it once you get into higher like circuit theory classes.
Yeah, and also the capacitor is very important since, like she said earlier, it's time dependent versus a battery will discharge at the same rate. Capacitors like allow you to mess with time in the circuit in a way which will become very helpful, which you'll see in the next project.
Okay, are there any other questions about capacitors?
Okay, awesome. So our next topic is integrated circuits. So circuits can get very complicated. This is a circuit for a 555 timer, and look at the schematic. That's messy, man. Like, how would you even put that on a breadboard? It's like so many transistors and resistors, and there's like even a diode in there. That's crazy. We don't want to deal with that. So instead of building these complex circuits, we can instead use integrated circuits. So integrated circuits are like an entire circuit just on a tiny semiconductor, generally made of silicon. And the benefits of using an integrated circuit is that it's small, it's cheap, and it's easy to replace, and they can be mass produced, and they're designed with one specific purpose in mind. So they'll all act the same way. And so they become very, very helpful.
And what's nice about these integrated circuits is that we can treat them like black boxes. We don't have to know what the IC does. Like, for example, the 5.5 timer, we don't have to know every specific detail about how the circuit works. We just have to know what happens when we put something in and what happens and what are we going to get out of it. So we're only focusing on the input into the black box and the output of it, which is really simple because you don't have to worry about really complex circuit theory or anything.
Yeah, so instead of having to worry about such a complicated circuit like this, all we get to do is look at this very beautiful, just 8 pins, all of which refer to different inputs and outputs. And it's just very easy for us to deal with. Very nice.
Okay, so a couple of things. We're going to be working with a 555 timer for our next project. So a couple of things about the 555 timer itself. It's really important to note the orientation of this IC. As you guys can see on the top left, or on this top image here, on the top right, there's going to be a little black indented dot, and then there's also going to be a little divot, and that indicates the top of the IC. And it's really important to note orientation because each of these pins has different capabilities and have different requirements for what you need to do with them. So obviously you don't want to be giving like the output pin an input reading.
Yeah, when you're building your circuit, basically you want to know exactly where ground is so your connect things to the right spot. And these are going to be there. These are often generally the way to determine the top for all different kinds of ICs. Some will either have, they can either have both, one or the other. I think for our project, our 555s have the little dot here. They don't have the semicircle. But yeah, generally that's always going to show the top.
And then it's just be really careful with these leads. They're a little bit more fragile than, say, a resistor or an LED. And then you won't have to deal with soldering in this project. Hopefully that's a breath of fresh air for you guys. But that is how you connect the IC to the the perk board is through this little socket.
Yeah, so in the future, if you find yourself soldering, try to use a socket instead of soldering the IC directly.
And that just is, the reason why you use a socket is because it's easy to interchange different ICs depending on what you want in your circuit, so that way you don't have to desolder all the time.
Yeah. Okay, does anybody have any questions about ICs? Okay. give me a thumbs up if you're feeling good, if you understand. Okay, awesome.
So now we're going to be talking about the 555 timer, which again, we're going to be using in our project. A couple of things, the 555 timer can be really helpful for different sort of functionalities. You can use it as a clock, a switch, use it for PWM, which is pulse width modulation. You can use it as a timer, etc. And it gets its name because there are three 5K resistors in the circuit.
Like we said, it's a black box. You don't have to worry about the circuit, but that's just how it gets its name. So a 555 timer has 4 basic modes that you can use it in. The astable mode, which is good for oscillation, monostable mode, which produces a pulse, bistable mode, which you can use as a flip-flop, and the Schmidt trigger, which you can use as an inverter. So we won't cover all of these. The one that we're going to be using for this project is the astable mode, but I have some links in later slides if you want to learn about the other modes. 555 timer is pretty cool. You can use it for a lot of stuff. It's one of the most popular ICs.
Okay, so here's a couple of important pins that you should note in your 555 timer. The first one is ground. Just like in your first project you had a ground, this is going to be what you're going to be connecting to the ground. Number 8 here, which is over here, is where you're going to be giving the power supply, like your battery. Number 5 is called the control voltage, and this is connected to ground. You're going to be needing a capacitor in this to connect with the control as well. And then we also have a reset here, and this just restarts the timer and sets everything to low. Or restarts the timer when it is set to low.
Yeah. So the reason it has a line over its head and reset is because that means that it's like the opposite. So instead of putting in 1 to reset it, you put in 0 or 0 volts to reset it. Just a fun fact. Also, yeah, so the control voltage is also helpful because it removes like fluctuation, noise from the environment. But sometimes we won't use it. So the second part of the project, we won't have anything plugged into this. But yeah, it just depends on what you're using the 555 timer for. And the rest of the pins, we have pin 2 is the trigger pin, pin 6 is the threshold pin, pin 7 is the discharge pin, and pin 3 is the output. So the trigger pin turns the output on when the voltage across capacitor 2 is less than 1/3 of our VCC, or the battery voltage, which is why capacitors are important, right? Because the capacitor will charge up slowly, so this will eventually slowly build to the point where it's less than this and then turn on. And then same thing, when it's greater than 2/3 of VCC, then it will turn off. And so then the threshold pin monitors the voltage of it and basically works to trigger the trigger pin. And then discharges the capacitor when VC2 is greater than 2/3 of the voltage, so that way we can reset to get into the first state. And then the output is the frequency that is then outputted by the 555 timer. So the output pin is the pin you're actually going to be using. The other pins make it work. The output is what we get from it. And
yeah.
I didn't follow what VC is.
Yeah. So we have it's kind of hard it's really hard to see, but we have a schematic here. It will come up later. So V stands for voltage, C2 stands for capacitor 2. So in this circuit, we have a capacitor here called capacitor 2. This is the same circuit you'll see in the project, so that's what it's referring to, this capacitor right here. Which is connected to the threshold pin.
So essentially all we're doing is we're going to just monitor the voltage across a second capacitor in order to do a particular function, in this case turn the 555 timer on or off. Okay, so in astable mode, which is the mode that we're going to be using for our 555 timer, it's going to output an oscillating square wave, which means that it's going to be on and off, on and off. And we have different thresholds with which it's going to be on or off. And low and high also referred to as on or off, respectively. So the frequency is determined by the capacitor's time constant, who can answer what the time constant of the circuit is?
Time constant of a circuit is the resistance times the capacitance.
Wow, great job.
Follow-up question. Follow-up question, how many time constants does it take for a capacitor to be fully charged? Yeah, 5. Perfect. That's a round of applause too. Okay, awesome.
Okay, so like I said earlier, here are some more resources, especially these videos. I really like these videos. The YouTuber is named Ben Eater. Really great videos. So if you want to learn more about how 555 timer works, you can go watch those. It's really cool. He makes like a full computer on a breadboard. It is really cool.
Yeah.
Hugely recommend. So now we are announcing our newest project. Very fun. Right too. It's the 555 timer, and we're going to be making it blink and making a piano with it. Due November 22nd.
We're not just working with LEDs and making things blink on and off. It's going to be a really cool project where you can adjust the pitch that your speaker is producing based off of the resistance and the capacitance, or the voltage across the capacitor. So it's a really cool project. The link to the spec is there, and we're also going to be having a work session next Thursday for it. So if you guys have any questions there as well, we're happy to help.
And before we go, I just have a few things that I want to cover that will be helpful in the project. So basically, once you build the circuit that we were looking at earlier, we have a formula here that will be able to give you the time on. So the length of the square wave for when it's on, so when the LED will be on, and then the time when it's off. And so that's 0.69 times the capacitance of the capacitor times the two resistors added together, and then the time off is 0.69 times C2 times R1, and that will produce something like this. And then for the piano part, and something that's important to remember is that a higher frequency equals a higher pitch, and that a low resistance means shorter on and off time and a higher pitch.
And it's important to also remember that frequency is the inverse of your period, and this period we will refer to is the period with which this 555 timer is on or off. So we can actually adjust the frequency of this 555 timer, and as a result, it'll produce a different pitch. So depending on how long your 555 timer is on, determines what type of pitch you're producing. So that's something important to note. 1/F is equal to T.
Yeah, and that's pretty much it. Thank you guys all for coming. Does anybody have any more questions before we go?
Yeah. You can come anytime. The lab is open, I think, from 10 to 6.
Oh, actually, that reminds me of something.
Yeah.
Some of the parts in this project are limited, so there's not enough for everyone to keep each of the parts, specifically the big capacitor you'll be using. So when you're done with your circuit or when you're leaving the lab, make sure you put the parts that you used back rather than just keeping them working in your box.
Yeah.
Is the lab going to be open tomorrow?
No, or I don't know. I don't think so.
Brandon, do you think it's going to be open?
Let me talk about it.
Okay, we'll send out an announcement
Maybe,
about
maybe
that.
not.
Yeah.
I just want to answer that question. I'm probably going to be there from 8 to 6, so you can come by.
Thank you, Alexi.
Thank you, Alexi.
Okay.
Air comfortably to Alexi.
Yeah.
Yeah.
Okay. Any other questions about this project or what we went over today? Okay, perfect. Thank you guys so much for coming. Again, that work social is going to have ice cream, hopefully, so you should definitely come out.
Hi, everyone. Thanks for coming. This is midterm.